Hello friends, welcome back to my channel. Today I'm going to discuss a numerical based on molecular diffusion. The numerical is specifically based on the case where liquid A diffuses in non-diffusing liquid B. In my earlier videos, I have discussed various aspects of diffusion through liquids, molecular diffusion through liquids, and in one of those videos, I have discussed the derivation for calculating molar flux or mass transfer rate for the case of liquid A diffusing in non-diffusing liquid B. Okay, so I'm giving a link to that video in which the equation was derived in the description section. So let us start the discussion. So we will understand a numerical, how to solve a numerical that is based on molecular diffusion in liquids, specifically for the case where liquid A diffuses in liquid B. Okay, so let us go and solve the numerical. First, we will understand what is the statement of that numerical. The statement for the numerical is like this. Acetic acid is diffusing through a stagnant water film 1 millimeter thick. The diffusion occurs at a temperature of 17 degrees Celsius. The concentrations on the opposite sides of the water film are 9 weight% and 3 weight% acid respectively. The diffusivity of acetic acid in solution is 0.95 into 10 to the power minus 9 meters square per second. The densities of 9 weight% and 3 weight% acid solution are 1012 kg per meter cube and 1003.2 kg per meter cube respectively. Find the rate of diffusion of acetic acid in water layer. Okay, so this is a case where you have two components. One component is acetic acid, whereas the other component is water. The diffusing component is acetic acid, and it is diffusing through a stagnant water film. That means the other component, water, it is not diffusing. The thickness of the film through which diffusion occurs, this is given to us. It is 1 mm thick. So straight away you can say this is the length of the diffusion path. This is the length of the diffusion path. Then diffusion occurs at a temperature of 17 degrees Celsius. Even though for molecular diffusion in liquids we don't need the temperature, but still they have given. That is not a problem. The concentrations on the opposite sides of the water film. So concentrations on the opposite sides of the water film, they are given to us. They are given in terms of weight% of acetic acid. So on one side, the concentration is 9 weight%, while on the other side it is 3 weight%. Then diffusivity of acetic acid in the solution is given to us. It is 0.95 into 10 to the power minus 9 meters square per second. And then densities of the two solutions, that is 9 weight% acid solution and 3 weight% acid solution, these are also given to us. So for 9 weight% solution, it is 1012 kg per meter cube, and for the other solution, which contains 3 weight% of acetic acid in it, the density is 1003.2 kg per meter cube respectively. So with all this information, we are supposed to find out the rate at which acetic acid diffuses through the stagnant layer of water. Okay, let us go and solve uh, this example or this numeric. So first, what is the case? I'm giving few steps. If you follow these steps, it will be easy for you to remember how to go for the solution. So first we will have to identify the case. After reading the statement carefully, first thing that you have to do, you have to identify the case, because once you identify the case, you will come to know which equations are to be used. So identification of the case is important. So this is molecular diffusion in a binary liquid solution. So binary system is involved. There are only two components, acetic acid and water. One component is diffusing while the other component is stagnant. Acetic acid is diffusing and water is stagnant. So for our discussion, we will denote acetic acid. We will let capital A represent acetic acid and capital B represent water. This is for our understanding. So A in the mixture is acetic acid and B is water. Now, whatever is described in the numerical, I have schematically represented over here. Okay, so you have two planes. Distance between these two planes is 1 mm. That is this is the water film. Thickness of the film is 1 millimeter. You have one end. You have acetic acid on this end, and it will be diffusing through the film, and it will be coming to this end. On this end, we know the concentration of acetic acid over here. It is 9% A by weight. So at this particular plane, you can say concentration is 9% E. Rest 91% is water. Then diffusion occurs from this end to the other end where concentration is 3 weight% of acetic acid. Okay, so concentration is taking place from a place of high concentration to a place of low concentration. So you can say on this plane concentration is 9% E. 9 weight% of E, and on this end or on this plane you can say the concentration is 3% of E. Of course the concentration is by in terms of percentage weight. Okay. Then at this end with this concentration of E, density of the solution is 1012 kg per meter cube, and with this weight% of acetic acid, 3 weight% of acetic acid, density for that solution is 1003.2 kg per meter cube. Okay, so this information is given to us in the statement. I have represented that pictorially. So if you call this to be end 1 and this to be end 2, let us call this end as A1 and this end as 2. Then after that temperature is given to us. Temperature is 17 degrees Celsius. So as a practice, you always convert it to Kelvin because you may need it. Sometimes temperature is required where in Kelvin. Over here, as I said, we don't need temperature in the calculation, but still, since it is given, I have written the thing. So T is 17 degrees Celsius, which you can convert to Kelvin by adding 273.15, which comes out to be 290.15 Kelvin. Okay, then next is DAB is given to us, diffusion coefficient of acetic acid in water. So this will be DAB. So it is given as 0.95 into 10 to the power minus 9 meters square per second. Further, this is what is given. This information is given in the numerical statement. We have identified the case, and now we know which equations are to be used. So the equations to be used are the equation to be used is we just need one equation to find out the rate of diffusion. So this equation will give you the rate of diffusion. So Na is equal to DAB upon Z rho upon MW average, which is the average value, into 1 upon XBM into XA1 minus XA2. So in order to use this equation, we need various values. The other value that is given to us is Z. Z is the length of the diffusion path, which in this case is nothing but the thickness of water film. It is 1 mm. So Z is 1 mm. I have converted it into meter, so it is 1 into 10 to the power minus 3 meter. Okay. So for using this equation to get Na, which is the rate of mass transfer, we need all the quantities on that are present on the right hand side of this equation. So DAB is given to us, Z is given to us. This is not directly given to us. We will have to find out this first. Then XBM is not given. We will have to find this also. XA1 and XA2, they are not directly known to us. So lot many things are supposed to be calculated first before you go on and use this equation. Okay. So uh, that's what I have listed over here. The following need to be determined first. We need to determine Xa1 and Xa2. We need to determine rho upon MW, average value of this group, and we also need to determine XPM. So first we will determine all this, and then we will use those values in this equation to get the final value for Na, which is rate of diffusion. Okay, so let us understand. The first thing that we will do, we will since we have to calculate XA1 and XA2, so first we will calculate these two. For that, again I have taken the schematic diagram which I just discussed on the previous slide. So if you look at end 1, I can write this at 1. If there is 100 kg of solution, there will be 9 kg of A and 91 kg of B. What, why this is the case? It is because the solution contains 9% of A by weight. That means if there is 100 kg solution, or in 100 kg of solution, the meaning of this 9% A by weight is in 100 kg of solution, there will be 9 kg of A and 91 kg of B. So we are writing this because this 9 kg of A we can convert to kilomole of A, and 91 kg of B we can convert it to kilomole of B, and that is what we will do in the next step. Okay, so XA1, that is mole fraction of A at end 1. So you can see how it is calculated. First, this will be mass of A divided by molecular weight of A at this end, divided by moles of A plus moles of B, total moles. Moles of A, mass of A divided by molecular weight. Moles of B, mass of B divided by molecular weight of B. So you have 9 kg of acetic acid divided by its molecular weight, which is 60. This divided by, again, weight of acetic acid, that is 9, divided by molecular weight of acetic acid, plus weight of water, that is 91 kg of water divided by its molecular weight. So if you simplify this, if you solve this, you will come to know that XA1 comes out to be 0.029. Okay. So in this step, we have learned, if we know composition in weight percentage, you can convert it to mole fractions by using this step. Okay. Similar calculations are done at the other end. So at the other end, by looking at this information, you can write in 100 kg of solution, there are 3 kg of A, that is acetic acid, and 97 kg of B. So again, using the same, you can say, approach, you can write the equation. So XA2, it should be 2. This you make it, you just, this is XA2 will be Ma upon, again the same formula, again same quantities, the quantities that are given to us, I have used those quantities, and if you calculate it will come out as 9.19 into 10 to the power minus 3. Okay, so XA1 is 0.029 and XA2 is 9.19 into 10 to the power minus 3. Okay, so that ends this step. So the objective of this step was to calculate XA1 and XA2, and now we have got those values. XA1 is 0.029 and XA2 is 9.19 into 10 to the power minus 3. Okay, then let us go to the next step. first step, the next thing that we need to do is we have to calculate average value of rho upon MW average. So let us understand how to calculate this. Again, we will refer the schematic diagram which was discussed previously. So at 1, if you look at in 1, you can calculate average molecular weight. Since at A1 there is solution of A and B, so the solution will have an average molecular weight, and we need to calculate that. How it is calculated? At A1, average molecular weight is mole fraction of a component into its molecular weight. So this is sum of product of mole fraction and molecular weight of the components. So we have just two components. So this is mole fraction of A into its molecular weight plus mole fraction of B into its molecular weight. Xa1 into Ma plus Xb1 into Mb. Now in the next step, this is again, if I have replaced Xb1 with Xa1. What is the reason for that? The reason is there are only two components. Two components are involved. So at end 1, sum of mole fractions will be 1. So Xa1 plus Xb1, it is 1. That means Xb1 is equal to 1 minus Xa1. And if you put all the values that are known, you get the average molecular weight as 19.22. Okay. So again, I would like to talk about this. Since there are two components, so Xa1 plus Xa2, I hope you have understood. If you have any doubt, you please mention that in the comment section. Okay, so you get the average molecular weight. Then once average molecular weight is known, you can calculate the value of this group rho upon MW average at in 1. So rho upon MW average at 1 will be density at 1 divided by average molecular weight at 1. Density at 1 is known, it is 1012 kg per meter cube. Average molecular weight at 1 we just calculated, it is 19.22. So this quantity rho upon MW average at 1 comes out to be 1012 divided by 19.22, which is 52.65. Similar calculations are done at N2. So at N2, first we will calculate average molecular weight. It will be Xa2Ma plus Xb2 into Mb. Again, in terms of Xa1, this will be written as Xa2Ma plus 1 minus Xa2 into Mb. If you put all the values over there, you'll get the final you'll get the value for average molecular weight. So MW average at N2 is 18.39. Then after that, we have to calculate this group. Rho upon MW average at 2 will be density at 2 divided by average molecular weight at 2. Density at 2 is 1003.2, and the average molecular weight is 18.39. So in this way, you get the value of rho upon MW average at 2. Now let us move ahead. Next, you just have to we just found out rho upon MW average is 52.65 and rho upon MW average 2 is 54.55. Now average of this value is required for us. So rho upon MW average value will be rho upon MW average at 1 plus rho upon MW average at 2 divided by 2. And if you put all the values that are known, that is 52.65 plus 54.55 divided by 2, which comes out to be 53.6. Thus, rho upon MW average value is 53.6. Then next step is calculation of XBM. So for that, the formula to be used, XBM is nothing but logarithmic average of XB2 and XB1, for which you have this equation XBM is equal to XB2 minus XB1 divided by ln of XB2 by XB1. But over here we don't know XB1 and XB2, So first of all, we will have to calculate that, and that will be calculated from x7. There are only two components. X7 plus xb1 is 1. So xb1 will be 1 minus x7. That is 1 minus 0.029, which comes out to be 0.971. Then xb2, again with the same understanding, it will be 1 minus xa2, that is 1 minus 9.19 into 10 to the power minus 3, which comes out to be 0.991. Okay. So finally, you just have to use all the values, that the two values, that is value for xb1 and xb2, to get xbm. So xbm you get is 0.981. Okay. So till this point of time, we have found out xa1 and xa2. We have found out rho upon mw average value, and now we have got a value of xbm. So knowing these three, now we are in a position to calculate the rate of mass transfer. So let us do that. So finally, we will calculate the last step in the solution is calculation of Na. So Na will be again the equation which I had already written on the first slide. So it is Na is equal to dAb upon Z rho upon MW average into 1 by XBM into xa1 minus xa2. Now all values are known to us. You just have to use the values. So DAB is 0.95 into 10 to the power minus 9 meters square. Z, the thickness of the film is 1 millimeter, which is 1 into 10 to the power minus 3 meter. Then rho upon MW average, the average value we calculated, it is 53.6. Then XBM, we have calculated it just now, it is 0.981. X7, we calculated it earlier, it is 0.029. XA2, it is 9.19 into 10 to the power minus 3. So all values, when we use them in the equation, all values should be used at their appropriate place, and uh, careful calculations will finally give you the value of the rate of diffusion. So your rate of diffusion, you are getting it in kilomole per meter square per second. So it is 1.028 into 10 to the power minus 6 kilomole per meter square per second. And that is the final answer that is expected from us. So this is how you can solve numericals based on molecular diffusion through liquids. So this numerical was concerned with case 1, where liquid A diffuses in non-diffusing liquid B. For the other case, I'll share in my next video. I'll be discussing a numerical that is based on case 2, equimolar counter diffusion of liquids A and liquid B. For time being, let us stop. Thank you for being with me. Please subscribe to my channel. Tell your friends to subscribe to my channel. I am going to share many videos on various important concepts of chemical engineering. For time being, thank you and hope to see you soon.